Hello my dear students. In the previous part of my lecture, I have already discussed about the basic introduction of nanoscience and nanotechnology. There, I had discussed the advantages and differences of nanoparticles over bulk particles, right? While discussing about various advantages of nanoparticles over bulk particles, I had discussed one special feature of nanoparticles, or you can say one great advantage of nanoparticles, and that is surface to volume ratio. I hope you remember and understood that part of my lecture containing the surface to volume ratio section. Now, in this part of my lecture, I am going to discuss another special feature of nanoparticles, or you can say one important phenomena of nanoparticles, and that is quantum confinement effect. While discussing about this effect, I shall discuss about little bit of the definition of quantum dots, quantum wires and quantum wells. Whatever these quantum dots, wires and wells, these are actually very fine, very small particles which are associated with this effect. So that is how, while talking about this particular effect, I shall talk about little bit of this quantum dots, quantum wires and wells. So what is quantum confinement effect? Before discussing about this particular effect in details, you just note down these particular points here. So in this particular first point, it is saying that this effect is mainly pronounced only when the particle size is very small. In this point, you can even remember one thumb rule. What that particular thumb rule says? It says that if the particle size is in the range of 1 to 10 nanometer, remember 1 to 10 nanometer, then only this quantum confinement effect is very much pronounced. Okay? Or alternatively, you can say that this quantum confinement effect is very much effective only when the particle size is in the range of 1 to 10 nanometer. So of course, one question that can come to our mind is, why this particular size range? Why this size range is actually so much crucial? What happens actually at this particular size range? Actually, when the size of the particle becomes that much small to be comparable to the wavelength of electron, their optical and electronic properties actually get drastically changed. Whatever the electron's wavelength here I am talking about, that is nothing but, you can also call it de Broglie wavelength of electron. You may heard about the de Broglie wavelength of electron, right? That famous de Broglie wave equation. What is that de Broglie wave equation? That is nothing but it is the lambda is equal to h by p. Right? What is lambda? Lambda is nothing but it is the de Broglie wavelength of an electron. H is nothing but it is the Planck's constant. P is nothing but it is the momentum of an electron. So you know already what is momentum. Momentum is nothing but it is mass into velocity. So here we can again write that this one is h by m into c. Right? It is the mass into velocity. So m is mass of an electron, c is nothing but it is the velocity of light. All these terms are actually constant term. So by putting all this particular term here in this equation, we can calculate the de Broglie wavelength of an electron. Even you can calculate de Broglie wavelength for an electron having kinetic energy 1 electron volt. So for an electron present in any particular shell having the kinetic energy 1 electron volt, for that particular electron, how will you calculate the de Broglie wavelength? So you just need to find out first the velocity from the kinetic energy equation, that is nothing but half mv square. You know already the kinetic energy equation, that is half mv square. So from there you can find out the velocity of that particular electron, and that velocity term you can put here in place of this c. And by putting that velocity term here, you can actually finally calculate the de Broglie wavelength for that particular electron having the kinetic energy 1 electron volt. So you just remember, for an electron having the kinetic energy 1 electron volt, for that particular electron the de Broglie wavelength is nothing but it comes out to be almost, it is 1.17 nanometer. Okay, you just remember that. Now the second point that to be remembered is, this effect is mainly related to solid materials. Okay, only to the solid materials. or you can say mostly in the case of semiconductor nanoparticles only. Okay, in some cases only liquid thin films also. Okay, mainly solid materials, or you can say that semiconductor nanoparticles, and rarely or in some cases this liquid thin films also. Now look at this very simple electronic energy level diagram of suppose one p block element or atom. So of course, if it is p block element, then it will have s and p valence shell orbital, right? So whatever the energy level here I am showing you is nothing but it is of course just orbital energy levels, right? This one is s orbital, this one is the p orbital. So whatever this particular atomic orbital's energy here I am showing you, this one is nothing but it is actually orbital energy levels, or simply it is just similar to the atomic orbitals, right? Now this atom, this particular atom can combine with another similar atom or different element, and it can give you a actually bonding type of structure, right? And finally many number of such type of actually combinations or many such type of actually elements or atoms can finally give you these types of solid materials or these types of actually bulk particles. Okay, so this solid bulk particle is having many number of similar atoms or elements in the form of repetitive basic units, right? So it is having a number of basic units, right? Suppose this one is a basic unit, this one is a basic unit having a number of atoms or elements. So in a solid bulk particle you will have many such type of actually basic units, something like this, like this one. This one is also one another basic unit, this one is also one another basic unit, this one is also one another basic unit, and all are having actually a number of similar atoms or elements. Okay, so of course all these similar atoms are present together in this particular solid material by forming some kind of bonding structure only, right? Such type of bonding structure is just similar to the molecular orbital, right? You may heard about the molecular orbital theory during your 10+2 or maybe during your 9+2 9 and 10 session only, right? So this one is just, this orbital diagram is just similar to the molecular orbital diagram only. Like this particular s orbital of this atom can combine with another s orbital of another element or atom, and it can give you one s bonding type of molecular orbital and one s anti-bonding type of molecular orbital. Similarly, this p orbital of this atom can combine with another p orbital of another atom which is not shown here, and it can give you 3p bonding type of molecular orbital and 3p anti-bonding type of molecular orbital, right? Now whatever these particular energy levels I am showing you, these energy levels are just for one combination only. Okay, in a bulk solid you have of course thousands or millions of atoms or elements, and of course all these similar atoms or elements will have similar energy levels, right? So if you draw all these energy levels at the same position, how it will be looking like? If you draw all these particular energy levels of all those atoms, millions of atoms or elements at the same position, then how it will be looking like? All those energy levels at the same position, it will be just looking like a continuum band, something like this. These all are actually continuum band. Okay, and of course the final structure is called band structure. This one is nothing but it is the band structure. It will be just looking like this. Many numbers of this s, suppose bonding orbitals, it can finally give you these types of band structure. This all many numbers of this, millions numbers of this p bonding type of actually energy levels together at the same position, it can be looking like something like this. It is also a band type of structure. So all these types of this bands, okay, this bands type of structure together can give you actually this whole band of this solid material. Okay, now you know already the highest energy level where electron can be found is known as highest occupied molecular orbital, or in short you can say that it is HOMO, HOMO. And just above to that energy levels, it is lowest unoccupied molecular orbital, or you can say it is the LUMO. In a simple way, you can say that this particular band, this dark one, okay, this particular band formed from highest occupied molecular orbital is nothing but it is the actually valence band. And whatever the band, this particular band, okay, formed from lowest unoccupied molecular orbital, this band is nothing but it is the conduction band. And whatever this particular difference, okay, whatever this energy difference between the valence band and conduction band, this energy difference is nothing but it is actually known as energy band gap, or simply you can say that this difference between the valence band and conduction band is nothing but it is actually the band gap. Okay, now depending upon the extent of this gap between the valence band and conduction band, okay, depending upon the extent of this particular gap, this solid material can be divided into three types. Number one is insulator. Okay, number one is insulator, where the gap between valence band and conduction band, this particular gap, okay, between the valence band and conduction band is very large, and that is how electron excitation from valence band to the conduction band is almost not possible here. Whatever the electron excitement or whatever the electron transfer possible from valence band to the conduction band, here in the case of insulator it is almost not possible. Okay, now the second one, this second one is nothing but it is the semiconductor solid particles, semiconductor solid materials, where the gap between the valence band and conduction band it is very less, and therefore whatever the electron transfer or whatever the electron excitation we have been talking about, that electron transfer from valence band to the conduction band, it is actually possible here in the case of semiconductor. Now at the last, the third one is nothing but it is also known as conductors, mostly metals, where theoretically whatever this particular gap between the valence band and conduction band, theoretically there is actually no gap between the valence band and conduction band. You may not see actually any particular gap between the valence band and conduction band in the case of conductors, mostly metals. Okay. So in this chapter, whatever we have been discussing is mainly related to this particular portion, this semiconductor portion, and whatever the band gap we can have for this semiconductor portion, that is nothing but that is also of two types. One is this one, direct band gap, and the another one, this one is the indirect band gap. Okay, for your just simple understanding, you just remember that this red curve, this red one, okay, this red curve is for highest occupied molecular orbital wave function, and this one, this blue curve, okay, this blue curve is actually it is representing lowest unoccupied molecular orbital wave function. Okay, which means both this HOMO and LUMO, both this highest occupied molecular orbital and lowest unoccupied molecular orbital energy levels, both are having actually this wave characteristics at k space. That is how those are actually something like wave functions. Okay. Now, if the highest point in the valence band, this one is the highest point in the valence band, and this one is the lowest point in the conduction band. Okay. So, if the highest point in the valence band lies directly under the lowest point in the conduction band, then in that way, whatever this particular difference between the highest point and the lowest point, this difference we can say that it is actually direct band gap. Okay. On the other hand, in this particular case, suppose if maxima and minima in the valence band and conduction band respectively appear at different points in k space. Okay, here this one is the lowest minima in the conduction band, and this one is the highest maxima in the valence band. So both are actually, both are different point at k space. So in this way, whatever this particular difference between these 2 points, this difference is actually known as, it is nothing but we can talk about an indirect band gap. We normally, for that particular difference, we normally talk about indirect band gap. Although this point, this point is also a minima point, okay, and this one is actually lie directly above to this maxima point, but this point, this minima point is not the lowest minima point. However, this particular point is the actually the lowest minima point. That is how in that particular case we will actually, whatever the gap we will assume, whatever the gap we will actually consider, that particular gap is nothing but we will consider the difference between this particular point and this particular point. And these both points are actually different at this K space. And that is how this gap is also known as indirect band gap. It is not similar to the direct band gap. Okay. Here, one important point you should remember is, since optical transitions are vertical in nature, here in this first point, you can remember that since optical transitions are vertical in nature, so the absorption at the indirect gap, so the absorption at the indirect gap will be weak, indirect gap will be weak, and transitions at the direct gap will dominate the absorption spectrum, and transitions at the direct gap will dominate the absorption spectrum. Okay, so what this particular point is saying, it is saying that since optical transitions are vertical in nature, okay, these optical transitions are normally vertical. That is how whatever the indirect gap we have been talking about, that in the indirect gap is actually nothing but the absorption at that indirect gap will be weak, and transitions at the direct gap will, of course, it will dominate the absorption spectrum. So whatever the absorption peak we normally see in the absorption spectrum using the UV visible spectroscopy, UV visible spectrophotometer, that is nothing but that is because of the direct band gap. Okay, suppose this one is your XY curve, XY axis, and normally we can have these types of absorption pattern we can see in the UV visible spectra, right? And this particular absorption pattern, it is nothing but it is because of the, mostly it is because of the direct band gap only. Okay. Now, if you see this energy level diagram in a reversible manner, something like this, you can see this continuum bands for bulk semiconductor particles, where you can see the gap. This gap is actually, it is very small. Okay, so for this bulk semiconductor particle, where you can see the continuum band, and whatever the gap between this valence band and conduction band, this gap is actually, it is very small here in this bulk particle. Now, suppose you want to decrease the size of this particular particle into nano size. So how will you do that? Of course, you will just break down this particular bulk particle into smaller one, something like this one, right? So by doing so, you are doing nothing but you are actually removing a number of atoms or elements from this particular particles, right? When you will decrease the particle from here to the nano size, so you will of course just break down these particular particles. While breaking down these particular particles, you are doing nothing but you are just removing a number of atoms or elements from here. So accordingly, whatever the associated energy levels here you have drawn initially, those particular energy levels will be also removed from here, right? Those particular energy levels also will be removed from here, from this particular band. So if some energy levels are eliminated from here, from these bands, okay, from these energy levels, practically what will you see? If some energy levels will be removed from this particular band, practically what will you see? you will just see some kind of discreteness, some kind of gap in between this energy level, something like this, right? Even within this particular band, you can see some kind of gap in between the energy levels. Here also you can see some kind of gap in between the energy levels. Here also you can see some kind of gap in between the energy levels, even within this particular same band. So whatever the continuum band initially we were talking about, okay, that one will not remain as continuum in the case of nanoparticles. Okay, and you will see of course some kind of some discreteness here at the edges of each band. These are actually some kind of discreteness, and you can see some kind of discreteness at the edges of each particular band. And this discreteness among these particular energy levels is more prominent in the case of nanoparticles only. This discreteness will further, actually you can see this discreteness will be further more prominent when you further decrease this particular size of the particle into even smaller one. Suppose from 8 nanometer to the 6 nanometer and then to the 4 nanometer. Accordingly, you are actually doing nothing but you are actually increasing the discreteness. As the elimination of these energy levels occurs mostly from the edges of each band, the reduction of particle size increase the band gap. Suppose from this one to this one, okay, from this bulk semiconductor particle to suppose this one 8 nanometer particle suppose. So accordingly the band gap is of course increasing from here to here, right? And if you even further reduce this particular particle into suppose 6 nanometer and then again to 4 nanometer and then to 2 nanometer, 1 nanometer and finally to the molecular level, okay, you are doing nothing but actually you can see the gradual increase of this particular band gap. Okay, this change of band gap is actually only possible at the nanometer level only. So whatever this particular change of band gap you are observing here, this one is possible only this at this nano range. One important point you should note here is, by reducing the size of the particle, we are doing nothing but we are restricting the motion of randomly moving electron within a restricted boundary. Okay, or alternatively you can say that we are confining the motion of electron within this specific energy levels. Suppose here in this particular case, electron can randomly move anywhere within this particular bulk particle, right? That means within this particular band, these are associated band. So within this particular band, it can actually move anywhere. But when we decrease the particle size to 8 nanometer, okay, and finally to the molecular level, the motion of electron will be of course restricted within this particular small diameter area only, right? This confinement of randomly moving electron within a small area, this one actually creates discreteness among energy levels, or you can say discrete energy levels. This discreteness is mainly visible only at even below 10 nanometer size of particle, which of course adversely affect the electronic and optical structure of nanoparticles. So again you can note another point, the second point, that the effect due to which the band gap energy of nanoparticles, increases upon reduction of particle size, is known as quantum confinement effect. So if you have to write about quantum confinement effect in one sentence, then you can write that the effect due to which the band gap energy of nanoparticles increases upon reduction of particle size is known as quantum confinement effect. Here, whatever the word confinement, the confinement means, even in the 3 point you can write confinement. It means to confine the motion of randomly moving electron to restrict its motion in specific energy levels. Okay, to confine the motion of randomly moving electron to restrict its motion of a randomly moving electron. That is nothing but it is the actually discreteness. Okay, and what quantum reflects? Quantum means the atomic realm of particles. That means the smallest possible discrete unit of any physical properties such as energy or matter. Okay, and that is how this whole phenomena is so called quantum confinement effect. Now, depending upon the confinement of electrons along any directions, nanoparticles can be classified into 4 types. Number 1 is, it is 3-dimensional nanoparticles. Number 2 is 2-dimensional nanoparticles. Number 3 is 1-dimensional nanoparticles, and number 4 is 0-dimensional nanoparticles. Suppose this one is a 3-dimensional axis. Okay, this one is a 3-dimensional axis represented for any particular particles, something like this. Okay, suppose along this side it is the x-axis, along this side this one is the y-axis, and this side it is the z-axis. Now, if any of the relative dimension is comparable with the de Broglie wavelength, or you can say if any particular dimension is actually below 10 nanometer, then the electrons movement actually are said to be confined in nature. Okay, suppose along x direction, y direction or z direction, whatever it is. Okay, if any one dimensions, along any one dimensions, if it is actually less than 10 nanometer, then whatever this particular electrons, those are actually said to be confined in nature. Okay, so if the confinement is only along one direction and remaining 2 dimensions are actually open for electrons free movement, then it can lead to the formation of 2-dimensional well type of structure, which is also called quantum well. Suppose here you can see whatever the restrictions of electron, means restrictions of electronic movement, that is actually mainly made along this z direction. Okay, that means along the z direction only the electrons movements are restricted. But if you see the x direction and the y direction, okay, along these 2 dimensions actually these electrons can freely move anywhere along these 2 dimensions, means x dimensions and y dimensions. So that is how these types of actually nanoparticles are also called what? 2-dimensional materials. Okay, so in the 2-dimensional materials the electronic confinement is along 1 dimension only, and whatever this particular electrons, it can move anywhere along the 2 dimensions. 2-dimensional materials means electron can move anywhere along the 2 dimensions, and here it is along the x dimensions and y dimensions. Electrons can move along the x dimensions and y dimensions. So that is how this one is called 2-dimensional materials. Okay, here you can easily imagine now whatever these electron restrictions, this electron restrictions is made along this particular z dimensions and along this particular y dimensions. So it means electron restrictions are made along the y dimension and z dimensions, and whatever these particular electrons, it can move only along this x dimensions. Okay, so that means electron can easily move along only one particular axis, and that is how this types of material is something, it is looking like wire type of structure, and that is how it is also called quantum wire, and these types of nanoparticles are also called one-dimensional nanoparticles. Now, if the restriction for electronic movement is made along all these three dimensions, something like this, here the restrictions is made along all these directions, right? Along the z direction also, along the x direction also, along the y direction also. It means here in this particular case, electron cannot move anywhere along any particular dimension. Okay, all these particular dimensions are actually below 10 nanometer, and that is how finally whatever the geometry it will give, whatever this particular size of the particle it will give, it is actually not more than 10 nanometer along any particular side. So it will give you a very small particles. So these types of particles are known as quantum dots type of particle, and these quantum dots type of particles are also called zero dimensional material, because along any particular dimensions the electron movements is not possible here. That means along any dimensions these electronic movements are actually restricted, it is confined. So that is how these very small, very fine particles along any particular dimensions are known as quantum dots type of nanoparticles, and these are actually nothing but it is the example of zero dimensional nanoparticles. Okay. So any cluster, colloids or nanocrystal having dimension less than 10 nanometer along any side are known as quantum dots. Okay. One well-known example of quantum dot is nothing but it is the fullerene. Fullerene you know already, you may heard about the fullerene. It is C60 carbon allotrope, right? So the diameter of this C60 is nothing but it is about 1.1 nanometer. Now, one fundamental difference between the 3D nanoparticles with the zero dimensional nanoparticle is, here in the zero dimensional nanoparticles we can have actually electronic restriction along any particular side. Okay, but in the case of three dimensional nanoparticles, electron can move anywhere along any particular directions. That means along any particular dimensions this size is nothing but, the dimension is nothing but it is actually more than 10 nanometer. Okay, so that is how the electron can freely move along any side, along x direction, along y direction and along z directions. Okay, so that is how these types of materials are also known as 3D materials. That means electron can move anywhere along any particular side. Okay. Now you can note down one example of these two-dimensional nanoparticles. One example is, it is two-dimensional nanofilm, ultra-thin two-dimensional nanofilm, or two-dimensional layer type of structures are actually example of these two-dimensional nanoparticles. On the other hand, any types of linear structure, okay, any kind of long linear chain type of structure, nanostructure is actually those are fall within this particular one-dimensional nanostructure category. Okay, so these are the references. You can also follow these references for more details, and then of course all the best and happy learning.